Okay. Can everyone see the text, like the screen that I'm sharing? It's good. Okay. Okay, we'll just wait a few more minutes. Okay, I think we can start. This week's paper is a bit more complicated than normal because it's really three different concepts merged together. I tried leaving a small summary on the reading reading groups channel. But it's basically about three things. One is the introduction of what they call meta SAEs, which are sparse autoencoders trained on the decoder of another sparse autoencoder. And they do this to try to measure how atomic the latents that each sparse autoencoder finds are. Then they do something else, which they call SAE stitching, where they train SAEs of different size, and they find they can add some latents of the bigger size to the smaller size, and this improves the performance, obviously, of the smaller SAE. And they to do this, they define two types of latents, what they call novel latents, which are latents that are in the bigger SAE but not on the smaller SAE, and reconstruction latents, which are in both SAEs, and sometimes there's more than one in the bigger SAE. That corresponds to a single one in the smaller one. The third thing that they introduce is batch top KSAs, batch top KSAEs are like top KSAEs, but instead of taking the top activations at any given token, they do it over a batch, meaning that each token can have a different number of active latents. They do this during training, where you train it with a certain batch size, and then when they're doing inference, they use a threshold instead of that they compute during training. So this is kind of a complicated. There's a lot of things in this article. The figures are not in the correct order. So I'm going to go over the figures and talk about the main results. I think it doesn't make sense to read the abstract because I just explained the abstract and would just be wasting time. And please, if you're going to write on the chat, at me, because I only have one screen, and that screen is looking at the same thing that you are seeing. So I'll not be able to. If you have questions, just interrupt me or at me in the chat, and I'll stop and look at the chat. Okay, so we are going, I think, following the order of the paper, of the figures in the paper. They start by discussing this concept of meta latents, which I think it's a very interesting concept, where, for instance, they find this latent that represents Einstein, and they train a meta SAE that tries to reconstruct like the decoded directions of the present SAE, and they train it to have a low average number of latents that are active, meta latents that are active. So in this case, they find that the Einstein latent can be interpreted, is constituted by these other 5 meta latents. German starts with an E, space and galaxies, science and scientists, and proeminent figures. And the reason that they do this is that they're trying to tackle this claim that SAEs are going to find atomic and complete. You can use SAEs to find an atomic and complete set of features that a model uses during its computation. And here they're showing that these latents are not really, or these features are not really atomic, and that you can decompose them even further. And after the atoms, you go to the electrons and the neutrons, etc. I don't know if other people have read the paper in detail or not. I think this result is interesting, but at the same time feels kinda obvious, because language does not have atomic concepts, right? When we think about Einstein, we also probably think about Germany or scientists or space and galaxies. And so it seems kind of expected that latents can be subdivided. The other thing that was kind of pushed under the rug, or at least not discussed enough. And you see, like, the order of the article is a bit strange because I have to scroll all of this to go to the actual part of the meta essays. Is that the reconstruction of the essays is much lower than that of a normal essay. Like the variance explained of a GPT-2 SAE with this size is closer to like 80-90%. And so this claim that meta SAEs are something real is I think a bit stronger than the evidence that they show. Like it's not obvious what meta essays are actually doing because they're not actually reconstructing well the decoder directions. Yeah, this was something. There's not much more about them about meta essays than this. They show, they have this graph where they compare the cosine similarity. So the meta SAE is trained on this larger SAE, on the decoder of this larger SAE, and they find that the latents that this meta SAE finds are closer to the behavior that they have is of a smaller SAE. So they basically find that this meta SAE is very similar. Is much more similar to this smaller SAE than to the SAE that it was trained on, which I think is interesting. But yeah, I don't have much stronger comment here. I don't know if other people have ideas, read this part of the paper, and have questions. One thing that I want to note is they did auto interpretability on these meta essays, and the way that they scored the explanations was by taking one sentence that activates that SAE and 4 sentences that don't activate that SAE. Sorry, that latent. And they ask GPT-4 to pick one of them, given the explanation. And they find an average accuracy of 73%, which is kinda the average accuracy that you'd expect for an SAE that is interpretable, but it's not a very good score. And 73% means that the explanations that they find for these meta essays are too general or too broad. And so again, I think that they show enough evidence that SAE features are not atomic, and that you can decompose latents into short other directions. But at the same time, it's not obvious if their meta SE results are the strongest.
I do have a question, if you don't
Yeah,
mind.
yeah.
So is my understanding correct? And so the way they train the meta SAEs is the inputs would be the decoder directions, and then they try to
Mhm.
reconstruct them with having a very low sparsity, like they say maybe 4. Is that
Yeah.
correct?
Yes.
And do we know if they do that for all the decoder directions, or if they pick ones that seem interesting to do? Because it seems maybe too much to train one meta SAE for each direction.
Yeah, I think they train a single meta SAE on all directions. So, so you see, we train our meta SAE on the decoder directions of this dictionary size using this dictionary size with an L0 average L0 of 4. Because there's only this number of samples, because they're actually doing the directions and not the activations. They have to train for a lot of epochs for it to converge, and that's probably, or that's maybe why the variance explained is not so good. Is that there's not enough diversity um, of the data set, I guess.
Okay, so it's a single meta SAE for each
Yeah.
SAE. Okay,
Uh,
all right, thank you.
yeah, it's a single meta SAE for each decoder. Yes, I think here on this part of the article, they only looked at a single SAE, at this one of size 49152. Um,
This
they
is,
didn't
oh, sorry.
go.
Um, is this for a single layer? Like, do they just stick to one layer, or
Yeah,
do they do the? Okay,
no. If I understood correctly, they just picked one layer. I forget where it says, but they just picked one layer and one size and trained the meta SAE here. They didn't investigate if you add a different dictionary size, what type of meta SAE you'd get, or if you did a different layer. Or I'm sorry, maybe they did, and this is in the appendix, but this is not really discussed in the main text. I vaguely skimmed through the reviewers' questions and the replies, and I don't remember reading that, but it is possible. Yeah, you see, meta essays, additional figures. Yeah, they don't talk about meta essays more, so they don't train it on different layers or of different sizes. Uh, this this article is really a combination of three different blog posts, uh, and then they merge them together, and so yeah, because of that they didn't have enough space to go deeply in each of the sub teams.
thanks.
Okay, so then if there's no more questions about the meta essays, we can look at the stitching. Um, the idea of of essay stitching. I don't know if this figure is helpful or not. Yeah. So right, this is more for the meta essays or for splitting, I guess. The idea of stitching is that you could train two SAEs a large one and a small one. And then you could try matching the latents of the large one to the ones of the small one. And the ones that you can match, and I will explain how they match them, but the ones that you can match, you call them reconstruction latents. And the ones that you cannot match is probably a novel latent, one that's not represented by the small SAE. And so what you can do is make an intermediate size between the small SAE and the large SAE that has this new novel latent. And if you want, you can even switch one of these. Here they switched L3 with L7. And now you have, say, a stitch SAE, which is a bit bigger than the small SAE, but smaller than the large SAE. And hopefully, and as they show, this one has a better reconstruction loss than the small SAE. And how do they do this matching? Where is the equation? Here. They compute the cosine similarity between each latent of the small SAE with each latent of the big SAE. And then they take the maximum of this cosine similarity. And so this means that for each I don't know how this is possible, but for each SAE, you have a threshold on cosine similarity, and if it's bigger than a certain threshold, you can pair them up. When you do the maximum value, you just have one pair, but basically you have a correspondence between latents on the large one with latents on the small one. And what they find is that there's some latents that don't have a high cosine similarity with the ones in the small SAE, and that's what they call novel. So all of these ones have a cosine similarity bigger than a certain threshold. In the case of GPT-2, they use the threshold of 0.7. But in the case of Gemma, they use the smaller threshold of 0.3. But because of this threshold, you either have latents that have pairs or latents that don't have pairs, and the ones that don't have pairs are what they call novel latents. And what they show, and the way that they find this threshold, or that they rationalize this threshold, is that you can individually add each latent of the large SAE to the small SAE, and run this augmented SAE and compute the mean squared error over a certain data set. And they find that if they add the latents that have low cosine similarity, they always improve the mean squared error. While if they add latents that have high cosine similarity, sometimes or most of the time, they increase the mean squared error. And if you think about it, and the way that they explain this is that if you add to the small SAE L7, for instance, without removing L3, and you don't train anything again, then on the data points that in the small SAE L3 fired and on the large SAEs L7 fired, you'll have both of them firing. And because they're very similar, you kind of overshoot. And so what they say is that if you want to do stitching, you can just, without any kind of replacement, so you can just augment your SAE with the ones that have a low cosine similarity. And if you want to add the ones that have a high cosine similarity, you should switch them with the one on the small one. So you switch L3 with L7. And then you add, this should be L9, I think, but it doesn't matter. Or L8 also works. And what kind of result do they get when they try this? They show that you can like interpolate between sizes and choose the L0 that you want, like in a kind of continuous way. So what they do is that here, this is the mean squared error of a 768 latent SAE with L0 of around 35, and they start adding the novel latents, meaning the latents that the SAE didn't take into account before, the ones that have low cosine similarity. And this phase here where the L0 is going up. Then they start swapping some of the reconstruction latents, which again decreases the L0. And they do this, let's say, iteratively, until at the end they went from a 768 latent SAE to a 1200 latent SAE. In there, this was something that I left as a comment in the reading group, and I haven't looked at the numbers closely. But on the original blog post, they showed, if you look at this point here, so the point right before you go over the size, this stitched SAE is better than the freshly trained SAE of the same size -1. But part of that reason, and I think that's why they didn't include that result here in this article, was that this stitched SAE has a slightly higher L0. And so you're in a different point on the Pareto frontier of mean squared error and L0. And so the comparison between the two is not quite there. You'd have to switch or fine tune the SAE to go down to the correct L0. And they don't do this experiment, and so it's not obvious what the result would be. Their justification of trying this out, and these results are maybe a bit old in the Mech Interp world, just because they're from some months ago and are kind of at the start of when people were doing essays. The idea here was is new how many latents were missing from small essays, and that's why they argue, and that's one of the things that's said in the abstract, that this paper is kind of trying to show that SAEs don't find or don't find a complete set of the features that a language model uses, and that they're not canonical in the case of they're not atomic in the case of meta essays. As I left the comment, as the comment that I wrote on the group chat, again, this is an interesting result, but that feels kind of obvious as well. If you wouldn't expect that larger SAEs would find new latents, there would be no reason or no expectation that they would perform better. And so it kind of seemed obvious that as you increase the size of the SAE, you'd always find new latents. They do show an interesting thing in the abstract, which I don't know if they even thought about that much. But here they show how many latents are new or reconstructed for different sizes. And so from here to here, they're going, they're always doubling. So 700, 1,500, 3,000, etc. So each of these steps, they're doubling the size of the SAE. And so when they double the size of the SAE, they find that close to 50% of latents are new. When they go from a small size to a slightly bigger size. But interestingly, when they go from a big SAE to double that SAE, the fraction of new latents is smaller. So only like 23% of latents are new between these two SAEs. And so the question that I posed is, okay, if you double again, and if you double again, if you double again, will you ever reach 100%, where the new SAE size does not find any new latents? Or do you only ever reach that in the infinite, let's say, width limit? Because here you're doubling the size, so it's not trivial. So you can maybe do 4 or 5 doubling steps, but not much more than that before your SAE has more parameters than PT5. And so I think they don't explore this idea enough, because there is a world where just making the SAE bigger would make it not learn new features. It's not obvious if that world is in the infinite width limit, which we don't really care about it, or if it's in a limit that could be actually usable, and this could define the size of SAE that should be optimal to find all latents or all features represented by an SAE. You'd still have a bunch of split features or of features that split from the smaller size, but maybe you could use some of these methods that they introduced to kind of distill this super big SAE into a smaller SAE, just by keeping all the novel ones and throwing away all the reconstruction latents. Yeah, I don't know if anyone has any questions about the stitching SAE part.
Yeah, so I suppose they discussed the possibility of having novel features when you go up in sizes between two SAEs, right? And So what they find is that in bigger SAEs there are novel latents. But do they
Yeah.
discuss the possibility that in smaller SAEs there are features that don't reappear in the bigger SAEs? Because if you go back to the interpolation figure, yeah, so it seems, for example, if you take the smallest one and then the second smallest one, it seems like so first they start by adding the novel latents, and then they start
Mhm.
swapping the other ones. So this figure suppose that at the very end of the first interpolation, they were able to swap all the latents from the smallest one. Do that mean that there is no latent that doesn't have a replacement in the bigger one?
Yeah, I don't think that they discuss that. Maybe they do, and I didn't find it. Um, I think the answer to your question is yes. Um, there will be some latents on the small SAE that don't have any pair on the bigger one, especially for smaller sizes, and that's mainly because it's like it's learning an intermediate direction or something like that. Like it's learning a principal component, which you can further decompose much better if you have more latents, because you need, like, if you're fighting for sparsity, it's just better to not use principal components anymore. Um, and yeah, so I think they don't discuss this. I think um, maybe if someone has a better idea, but I'm pretty sure they don't talk about the fact that some in the small one don't appear on the big one.
And do you think they just throw them away before moving to the next size in the figure?
I'm not sure.
Okay.
I think they probably ignore them, and they so at the end this one has probably a bigger size than the original one. But there's very few latents that would have this property. Um, so maybe it, it the size doesn't grow that much, and especially for these
You,
bigger
you, you,
sizes,
s-
it will be less of those.
you said in the blog post they said that they showed that just before moving to the next one, they were able to obtain better reconstruction. Maybe that's related?
Yeah, my my opinion, but it may be wrong, is that the reason that their Frankenstein SAEs and their SAE of the largest, the next size, the Frankensteins are better, is because DL0 is higher, and they do mention this. So you see, for example, this one has an L0 of 53 versus an L0 of 35. Or here, this 1000 something, has a double the L0 of this one. And so, yeah, if you have in mind like the sparsity L0 curve, you can start imagining that maybe this difference could be in, at least partially just due to the fact that the L0 is double. Is there Does anyone have any other questions, comments about the stitching part? If not, then the last section was on batch stop K. And batch top K, as explained in the introduction, it's like top K, except they only keep the top K times the size of the batch activations for each token. And this means that when they train it, which I'm not sure where it says, I think only on the appendix, they train it with a certain batch size, but then while training, they compute these thresholds that that's the expected threshold that would get the wanted sparsity over this imaginary batch. Because when you're doing inference, you don't have the batch anymore, and instead they use this threshold, and so it looks closer to the jump ReLU case. So they train it like a top K, and then they do inference like a jump ReLU. And they basically show that it's just better than top K for everything that they tried. So for the same dictionary size and the same average K, batch top K was better, was even better than jump ReLU for the case that they tried, and for the they don't show here the dictionary sizes, so we cannot see the trend, but here they try a specific dictionary size in different case, and they show that batch top K is better than even jump ReLU. And yeah, that was this paper. I think we covered a bunch of different topics. So if people have questions, please. I'm not as good as Alice as at looking at names and asking questions. But yeah.
Sorry, I put a question in the chat. Oh.
Yeah, I'm not sure about so the justification to do batch top K is that it feels for us humans that maybe you don't need to always have K latents for any token, and that maybe you could use more latents for some tokens and less latents for other tokens. The reconstruction loss that we are having is still so bad that it's not obvious that this intuition holds, but still batch top K just feels better. I think they only train it on the residual stream, and so it's not obvious that this improvement would also hold for the MLP, and it's not obvious that it would also hold for transcoders. But it feels like a not that complicated implementation over just normal top K. So yeah, I think batch top K feels better.
Yeah, I can try it like today. It seems like one line of code or something.
Yeah, I think the only thing that you'd have to do is like the threshold computation beforehand. But yeah, it makes
Yeah,
perfect sense.
just to see if like the FVU is lower, I might just be super lazy and not even implement that. And then if the FVU
Yeah.
or just like if the FVU is lower, then we could like, you know, actually, yeah. Anyway.
Ned said it makes sense that batch top K would be better. If you think of K as a threshold, then the algorithm would choose a different threshold to adapt to the data distribution instead of a fixed threshold chosen a priori. Yeah, I think that's
sorry.
Go.
Can you hear me? I'm never sure if my microphone is working.
We can.
On which computer I'm on. Okay, great. Let's see. Yeah, so yeah, that's. I think this makes a lot of sense, and it's just surprises that it wasn't done earlier. I guess yeah. So that's. I think also let's see. I do believe there's similar like Vista and Vista, all these sparse coding algorithms. I do believe many of them do provision for some kind of adaptive threshold as you go through the iterations to when you're just trying to do a sparse regression solver. Like they will often adapt the threshold as they go through each iterations. So that makes a lot of sense if I'm understanding how this works correctly, and I may not be. So that was maybe one comment.
Yeah,
I mean,
so at the end of the day, the threshold is fixed, but
then maybe I'm totally wrong. I'm sorry.
No, but you're right. You're right. So the threshold is fixed in a way that K is not fixed.
Understood. Yes. Okay.
So yeah,
that's interesting. Okay.
I think they don't compare it here, and I don't know exactly the implementation, and I don't remember the details on Gemascope, but in Gemascope they do discuss a jump ReLU where you do inference time optimization, where you optimize the threshold.
Yeah, that's okay. That's an example. That's a good example. Yeah.
But even though it's the same group, I don't know if this jump ReLU comparison has ITO or not.
Right.
And yeah, it's not obvious. Sorry, I think doing adaptive stuff is interesting and probably is not explored enough. But all these groups like Neil and people from his math stream and other people at DeepMind, I'm assuming, have been looking at these problems and all of these. So batch top K I think came out like the week after top K, and then jump ReLU at the same time because it's just the same thing. You just train it differently.
Sure.
So the fact that there still haven't been optimizations at inference time is maybe like a signal that either people didn't explore enough or that it didn't get that much performance boost.
Yeah,
I do think one. Oh, sorry.
Go ahead. No, go ahead.
I was just gonna say, I think one problem. I mean, maybe it can be solved. It's not really clear. One problem with batch top K is that you at least can't use Leo Gao's Triton kernels for this. I'm just like looking at my own code and seeing what I have to change. And so it's going to be slower because of that. And it seems like there might be kind of like a fundamental issue here where like if you have a fixed K, then it's easier to write like a kernel that like does things more efficiently. Whereas if it's like not fixed, it's like a bit, I don't know. I'd have to think about it a bit more.
So I don't know if there's no Ned. Were you saying something?
Yeah, I guess I just want to go back. I sort of I have to admit, I just didn't really understand like the I definitely agree with the first two parts of the paper where like they were doing, ways to find structure that's probably missed by just doing a single, like a single sparse linear combination of latents, like a single SAE. And I think there's just like considerable evidence from many different places that yeah, like there it's something is missing if you just try to do a single sparse linear
Yeah.
combination, right? And this just kind of seems like more proof of that, and maybe an interesting method of sort of finding some clues as to what that structure might be. Um, is there any kind of, I mean, I sort yeah, there's a lot of stuff to go through for this paper, so I didn't quite read it all, but I was like, is there any speculation that anyone saw about like, like, hey, maybe this is not like the be all end all, like these meta SAEs, maybe they're just like an important line of evidence, but probably they're not the final method on this, but like, do they give any speculation about, maybe this would lead to a newer method that or maybe just take the SAEs as like the first step, and then you do some kind of further algorithm on them to find, some nonlinear feature or whatever. Like, is there anything like that in there? I mean, I think your comments also were really on point about this idea that like, okay, it's not really surprising that Albert Einstein is not an atomic concept. It's like, are atomic concepts even real, right? Like nobody knows. Like,
Yeah.
it seems like the answer is probably no, but you know, I don't know. That was maybe a thought there.
Yeah. So I think I don't want to speak what was on the mind of the authors. But I think here in this paper, these were kind of old results that were not, each of them was not enough to an individual paper maybe, and they like stitched them together because a lot of these authors were the same people in different works, and so I think it definitely doesn't have the depth to answer the kinds of questions that you were making of, okay, what's the next step, what's wrong. It's mostly saying, okay, we shouldn't think about SAEs, about SAE features as atomic. We shouldn't probably even think about them as like complete, which they show partial evidence for, but not complete evidence if there is complete evidence. But yeah, I don't think they point to anything. Let's do something better. It's mostly just pointing the negatives, which I think is, I mean, it's a valid thing to do when you don't when you don't know where to point.
I do agree, and so the example they show with Einstein is they use the meta SAE to find other more atomic features. But one of the features is the one I think it was starting with E. I would argue that this one is maybe less atomic than Einstein because like you'd find more words that I mean even the other ones, and the fact that they can decompose Einstein to other features. I don't know if it shows that Einstein is atomic, or on the other hand, or maybe even um, yeah. So what I mean to say is I don't agree that using meta-essays to find other features is enough evidence to show that there's a concept of atomic features. And even if you consider atomic, on what level? Is it like on the semantic level, or is it on other levels? So yeah, it's maybe an abstract notion for something to be atomic, for a feature to be atomic.
I think they're also arguing exactly that. I mean, maybe they don't go into the philosophical, let's say, reasoning behind it, but they're for sure pointing out that you shouldn't think about them as atoms. Like if you go the meta level and you train a meta SAE on the meta SAE, you'd probably find loops where maybe on the start with T latent, you'd find the Einstein latent as well. And so it's obvious. The concept of atomic feature seems like not possible if you just think about language in general. But it would be, let's say, possible if you had an infinite width SAE, where you'd have one latent per data point, right? Top K1, one latent per data point, and those would be atomic for that data set. But yeah, otherwise it doesn't really make sense. Like in any usable, interpretable for a human way, I don't think you could ever consider them atomic. Okay, so we reached the 1 hour mark. If there's no more questions or comments, I would stop the reading group for today. Thank you for coming. And please, if you well, next week we already have we'll have Arnin presenting, which is it's going to be her own work, so it's going to be better presented than this week, because it's going to be by people that made the work. So I hope to see you next week.
Thank you. Bye.
Bye.